Welcome back, students. Today we are picking up where we left off in the last lecture. In the last lecture, we evaluated the total differential for the internal energy. Today we are going to do the same thing for the enthalpy. In the process, we're going to figure out how we can calculate enthalpy as a function of pressure and temperature. We're also going to see how we can show the relationship of the constant pressure heat capacity to the constant volume heat capacity like we've been doing. And then at the end, we're going to look at a practical application of all of this stuff to show how changing the volume of a gas actually can affect its energy and its temperature. The learning goals for today are going to be to explain, just like last time, we're going to explain now why it's fair to assume that enthalpy is only a function of temperature. And at the end, our practical application that we're going to use is we're going to be able to explain how refrigeration works. So we know our refrigerators are cold, and what actually makes the refrigerators cold is the expansion of gases. So we'll see how that takes place. Just like last time, we're going to spend most of the time on the whiteboard in this video since we're doing a lot of math. In the last class, we described the change in the internal energy as a function of volume and temperature. We did this not because we had to, and the volume and the temperature are the only things that affect the internal energy, but simply because these are the simplest variables that describe internal energy. So when a system changes with respect to volume and temperature, it also changes with respect to pressure. But we don't need to account for the pressure because by accounting for the volume and temperature, we've also accounted for the pressure because those three variables are linked with the ideal gas law. Since enthalpy is related to the heat at constant pressure, it turns out that it is easier to describe the change in enthalpy with respect to temperature and pressure. So we say that enthalpy is a function of temperature and pressure. And if we want to know the total differential of enthalpy, we would say dH is equal to the partial derivative of enthalpy with respect to temperature at constant pressure times the extent of the temperature change plus the partial derivative of enthalpy with respect to pressure at constant temperature times the extent of the pressure change, like I have written here. Now, we're going to go through the same process to solve this that we did last time. We'll start by recalling that the enthalpy changes with respect to temperature. That is the heat capacity, and specifically, it is the heat capacity at constant pressure. So we already have an expression for the partial derivative of enthalpy with respect to temperature at constant pressure. It is simply the constant pressure heat capacity. What can we say about the partial derivative of enthalpy with respect to pressure? We're going to have to use our thermodynamic definitions to come up with a solution. We'll start with the fact that we based enthalpy off of the following. So that enthalpy is equal to the internal energy plus PV. So if we want to know how enthalpy changes, we can say that dH is equal to du plus dPV. dPV, since P and V are both functions, we have to use the product rule for taking a derivative. dH is equal to du plus PdV plus VdP, using the product rule to expand dPV there. What we'll do now is set these two different definitions of dH equal to each other to figure out what we can say about dH, dP at constant t. So we have one expression of dH here. We have a second expression of dH up here. So we'll go ahead and say that the partial derivative of enthalpy with respect to temperature at constant pressure dt plus the partial derivative of enthalpy with respect to pressure at constant temperature dP is equal to du plus PdV plus VdP. We'll now substitute in the definition for du that we came up with last time. So we'll say that du is equal to CV dt plus the partial derivative of internal energy with respect to volume at constant temperature dV plus PdV plus VdP. What we're trying to do is identify the partial derivative of enthalpy with respect to pressure at constant temperature. So that means we're considering a constant temperature process where delta T is equal to 0. In that case, these dT terms don't appear because there's no change in temperature. So what we can say then is that the partial derivative of enthalpy with respect to pressure at constant temperature dP is equal to what we have remaining, which is the partial derivative of internal energy with respect to volume at constant temperature dV plus P dV plus V dP. What we really want is just this guy here, so we'll divide both sides of this equation by dP, and what that looks like when we do is we cancel out this term, we'll cancel out this term, and then what are we going to do with these dVs? Well, we're going to have a dV dP, and this is an isothermal process at constant temperature. So what we end up with then is the partial derivative of enthalpy with respect to pressure at constant temperature is equal to the following. So we've factored out these two guys here. We'll have the partial derivative of internal energy with respect to volume at constant temperature plus the pressure. And then we have a new partial derivative. That's the partial derivative of volume, these two terms up here, with respect to pressure at constant temperature. And then we'll add in the volume. What we'll then do is plug in our expression from before for what du dv at constant T was. So in other words, what ends up in this brackets is the following. We have T times dP dt at constant V minus P. This is our internal pressure. And then we have a plus P. So these two terms will cancel out. So what we get then is the partial derivative of enthalpy with respect to pressure at constant temperature is equal to T times the partial derivative of pressure with respect to temperature at constant volume times the partial derivative of volume with respect to pressure at constant temperature, and then plus the volume here. To make this into its most compact form, we will use the two rules we had for working with partial derivatives last time. And remember that rule, one of them was the cyclic rule. So the cyclic rule said that if we had dP dt at constant volume times dV dP at constant temperature times dt dV at constant pressure, all of this ended up being equal to -1. So we have two of those guys right here, and what we'll do is divide both sides of this equation by dt dV at constant P. And what we'll get when we do that uses our second rule, so this will cancel out from this side of the equation, and on the other side of the equation, we're going to have the inverse. So what we can say then is that the partial derivative of pressure with respect to temperature at constant volume times the partial derivative of volume with respect to pressure at constant temperature is equal to negative the partial derivative of volume with respect to temperature at constant pressure. And so we can go ahead and plug this guy in here to have a nice compact form of the partial derivative of enthalpy with respect to pressure. So we do that, we get the partial derivative of enthalpy with respect to pressure at constant temperature is simply equal to V minus T times the partial derivative of volume with respect to temperature at constant pressure. For ideal gases, we have only been considering the enthalpy as a function of temperature. In that case, we expect this dH/dP at constant T to be 0 for an ideal gas. Let's see if that is the case. The ideal gas law tells us that the volume of a gas is related to the temperature by nRT over P. So the partial derivative of this volume with respect to temperature at constant pressure would simply be nR over P. And if we plug this in up here, we get V minus T nR over P, which is the same as volume. So we get volume minus volume equals 0. So it is 0, just like we would expect. For real gases, this is going to have a number. For solids and liquids, they don't really change very much with, their volume doesn't change very much with respect to temperature. So the change in enthalpy with respect to pressure is approximately just the volume for solids and liquids. The next thing we'll do is evaluate this relationship of heat capacities that we've been using up until now. We'll start by looking at a formulation of the first law of thermodynamics, where we say dq is equal to du minus dw. If we plug in our expressions for du and dw, we'll get that dq is equal to cv dt plus the partial derivative of internal energy with respect to volume at constant temperature, dv, and then dw is negative p external dv. Since that's negative, we have positive p external dv. What we'll be considering here is a constant pressure process, because we want to relate this to the constant pressure heat capacity. For a constant pressure process, we're looking at dqp, and we already know that that is equal to cp dt. So now we have some relationship between the constant pressure heat capacity and the constant volume heat capacity. We'll go ahead and pool these together. We'll have that cp dt is equal to cv dt plus the partial derivative of internal energy with respect to volume at constant temperature plus p dv. Now I have p instead of p external because we are at a constant pressure. So there's only one pressure for this. So the external pressure is also the pressure. Now, what we'll do is the same trick that we have done above to relate this here into terms of things that's just based on pressure and temperature. So with that, I'll get cv dt plus t times the partial derivative of pressure with respect to temperature at constant volume dv. We'll then divide both sides of this equation by dt. So we'll divide by dt over here and dt over here. Remember, we're considering a constant pressure process. So that gives us Cp is equal to Cv plus T times the partial derivative of pressure with respect to temperature at constant volume times the partial derivative of volume with respect to temperature at constant pressure. So we have this nasty stuff here. Now, what is this for an ideal gas? Let's go ahead and evaluate it using the ideal gas law. The ideal gas law says that PV equals nRT. So that means that P is equal to nRT over V, and V is equal to nRT over P. So if we're taking the temperature derivative of both of these guys, we have Cv plus T, and then this first one here, dP dt at constant V, is simply going to be nR over V. And the second one, dV dt at constant P, is going to be nR over P. So plugging these in here, what we'll end up with is Cv plus, and I'll write it this way, I'll write nR times nRT over PV. This here is basically, this is the ideal gas law. We know that PV equals nRT. So this whole thing ends up being equal to 1. Therefore, we have the relationship of Cp equals Cv plus nR. If we want to put this in molar units, we need to divide by the number of moles. And that's going to give us the molar heat capacity, Cpm per mole, is equal to Cvm plus R. And this is the relationship that we've been using. If we don't have an ideal gas, we can't necessarily say these things that we've been doing. So we'll have to use our beta and kappa constants that we've been using. And for that, we have Cp is equal to Cv plus Tv beta squared over kappa, where beta and kappa are these constants that are related to these two partial derivatives up here. The last thing we'll cover today is the Joule-Thomson experiment. This experiment shows what happens when a real gas is expanded. Those of us who have used compressed nitrogen know that the valve gets cold as the compressed gas is expanded. Compressed hydrogen is actually the opposite, where the valve will get hot as hydrogen gas is expanded. And to do this, we're going to go back to these slides. Here we have the setup for the Joule-Thomson experiment. So we have a piston assembly where we have a gas on the right side here at a pressure, volume, and temperature. This gas is compressed where it goes through this porous plug, and it's expanded on the other side, such that it's at a new pressure, volume, and also potentially temperature. How can we describe what goes on in this process? If we assume that this is an adiabatic piston, the internal energy is equal to the work. the total work is going to be equal to the work done on this side and then in this side of the process. So let's go back to the board and look at how we can describe the work for this process. The total work is equal to the work done on the left side plus the work done on the right side. Since these are done under constant external pressures, they're simply equal to the following. So on the left side, the work is equal to the negative integral of that first pressure times the change in volume. And the change in volume is going from the initial volume down to 0. The work on the right side is equal to the negative integral times the second pressure. It's always at that pressure, dV, and that is going from 0 to the final volume. So plugging in these numbers, we get that the total work is simply equal to P1 or negative P1 times 0 minus V1 and then minus P2 times V2 minus 0, or P1 V1 minus P2 V2. Like I mentioned in the slides, the internal energy change here is equal to the work because this is an adiabatic process where the heat is equal to 0. So delta U is equal to the work, and delta U is also equal to U2 minus U1. So here we have U2 minus U1 is equal to P1 V1 minus P2 V2. If we rearrange this, we end up with the following. We have that U2 plus P2 V2 minus U1 plus P1 V1 is equal to 0. Now, this should look familiar. This U plus P times V is our definition of enthalpy. So this is telling us that H2 minus H1 is equal to 0, and H2 minus H1 is, of course, delta H. So this is an example of an isenthalpic process where the change in enthalpy for this process is equal to 0. We can label a term here that is the Joule-Thomson coefficient, and the symbol we use for that is a mu, and then we put a JT here for Joule-Thomson coefficient. And this is equal to the change in temperature with respect to pressure at constant enthalpy, which is what's going on in this experiment. So we have a temperature change in this experiment as a function of the pressure change at constant enthalpy. And that is this value here, this change is defined as the Joule-Thomson coefficient. This is something that can be measured, and we can use this to get an estimation for the change in enthalpy with respect to pressure at constant temperature. So with this, we can say for this process that dH is equal to Cp dt plus the partial derivative of enthalpy with respect to pressure at constant temperature times dP. And this process is isenthalpic, so this is equal to 0. In this case, we can rearrange this, and we will find that the partial derivative of enthalpy with respect to pressure at constant temperature is equal to negative Cp times the partial derivative of temperature with respect to pressure at constant enthalpy. And that's just what we've defined as the Joule-Thomson coefficient. So it's equal to negative Cp times the Joule-Thomson coefficient, which is something that's measured experimentally, and we can go ahead and look up. The Joule-Thomson coefficient can be positive or negative. If it's positive, that means that enthalpy will increase as pressure decreases, and the gas will cool as it expands. If the constant is negative, the gas will heat as it expands. Here are some examples for some Joule-Thomson coefficients, and you can see that nitrogen that cools as it expands has a positive Joule-Thomson coefficient, and hydrogen has a negative Joule-Thomson coefficient, which is why it heats up as it expands. This is useful because it is used to do things like liquefy gases, if you ever wondered how they obtain liquid nitrogen, and also, like I mentioned in the beginning, for refrigeration. The way that liquid nitrogen is made is that gaseous nitrogen is fed first into a compressor that compresses the gas, and then it goes through a cooler, so it's cooled here, and as it expands as it cools. So we have this process of cooling and then expanding to lower and lower pressures, in which case the gas cools more and more and more. And as it does this, eventually this gas can cool so much that it in fact liquefies. The gas that doesn't liquefy is still very cold at the bottom of this and adds more cooling to the new gas that's being pumped out. And then it eventually will cycle back into the compressor and repeat in the cycle. So we can have nitrogen actually be liquefied in this process. This would not work for an ideal gas because ideal gases don't change temperature or energy as a function of the pressure change. So this will only work for real gases. A very similar thing is done in refrigerators. So your refrigerator has a compressor in it. That's that motor you might hear for your refrigerator. It pumps gases, and those gases are expanded. And as those gases are expanded, they cool. And that is the cooling that is provided in your refrigerator. So you use energy to compress the gas, and then the gas cools, and it provides a cooling effect to keep all your various goods in your refrigerator cold. So the conclusions for this section are that we can use this language of partial derivatives to inform us on how state functions change with respect to a single variable. And you can put these things together to figure out how they change to two variables at once by considering each independently. The internal energy and also the enthalpy of an ideal gas depends only on its temperature. But for real gases, that have real interactions, we consider them as a function of temperature and volume. We also consider the function of enthalpy as they change based on real gases, and that changes as temperature and pressure. Now remember that all of these gases, if I change the pressure of a real gas, I'm also changing its temperature and volume, so I would affect its internal energy as well. We just most commonly use temperature and volume variables to describe that. And the main thing is that most real gases will cool as they expand, which allow things like liquefying and refrigeration, although not all gases do that. But all real gases do change temperature as they expand. With that, I will let you guys go, and we'll go through some examples of this in class.